LearningMeasure.tv, Science and Engineering podcast with emphasis on measurement, brought to you by David Archer and LearningMeasure.com. Episode -2, Noise in the Cosmos. Hello, welcome to episode -2 of the LearningMeasure.tv podcast. I'm David Archer. I hope you liked our new intro. We're still learning about these sort of things. Like I said, the first five or six we thought it would take to learn how to produce these, and we're still learning. Sorry about the interview last week. We're still working on that too. But if any of you want to be part of our consultant network, you're entitled to be interviewed on the show so that you can tell people what you're looking for in terms of consulting contracts. And I'd like to say up front again, this time we're still looking for vendors or suggestions, and we'll talk about that towards the end. This week we're going to talk a little bit, well, obviously you've seen the title of this, is Noise in the Cosmos. We're going to start out by talking a little bit about noise measurements, and then the second half of that we'll talk about a particular application. We may do this over 2 episodes depending how well it goes. Okay, we're going to start off with noise. Noise power delivered, let's say, from a resistor. Most engineers have seen the equation. The power received is going to be K T B, where K is Boltzmann's constant, T is the thermodynamic temperature measured in Kelvin, and B is the bandwidth. Now, this is approximately true. You can just see from the form that something's wrong with it right away. If an infinite bandwidth, let's say you don't have, like you sit a resistor there and you have no filter, in an infinite bandwidth there's an infinite amount of power and an infinite amount of energy, so that just can't be possibly right. But you can still define the noise temperature this way. Okay? The noise temperature, doing a little algebra, noise temperature then is defined as the power per unit bandwidth divided by Boltzmann's constant. Now, so you measure some power per unit bandwidth, divided by Boltzmann's constant, you get something called the noise temperature. Now this of course, is a function of frequency. But if you want the noise temperature to be related to the physical temperature, and it's approximately true for microwaves for sure, there is a correction that can be made to this expression. You just add a term, usually denoted by eta. This is a function of frequency and temperature that keeps this thing from blowing up over an infinite bandwidth. Of course, this wouldn't now be the noise temperature, it would be the physical temperature measured in Kelvin. You have to, for precision measurements, you do have to include that term in your analysis. We're not going to say much more about that in this episode. If you want more information, check out our course, Measurement 403, Basic RF and Microwave Noise Measurements, on the LearningMeasure.com website. But we're going to go back to this. We're going to talk about measuring it now. Now, how you make a noise measurement system. Okay. Let's say you have some noise source at some temperature. Let's call it T, some noise temperature. You want to measure the power per unit bandwidth, or just the power in a given bandwidth, so you can compute power per unit bandwidth. You have some power meter of some sort. Okay, you're going to measure some power, PM. Unfortunately, with this setup, there's going to be some noise generated by the measurement system itself. You're going to have losses due to the transmission lines, mismatches, and you also have the problem that since the transmission lines are at finite temperature, they also contribute to the noise as well as take away from the noise power. I'm not going to talk about that too much. We're just going to assume you know how to do that. So now you've got the situation, well, the measured noise temperature, we'll call that the measured temperature, is the noise temperature of the thing you're trying to measure plus the noise of the measurement system, which we'll call TS. Now this is ignoring all the terms I said before, mismatches, loss terms. We're going to speak in generalities. Like I said last time, in any measurement, the devil's in the details. Well, in order to actually, if you knew this, you could subtract it from your measured value to get the value of this thing. Now typically, the noise in any measurement system is pretty high relative to something you're trying to measure. I mean, that's what this typical case you're in. So you want to find out what the system noise temperature is. Well, one way to do that is in your measurement system is to deal with a known standard. You know, you could have a T standard and you could measure the noise and subtract them, but that's typically not how it's done. Typically what you do, and there's all kinds of reasons for that, mainly the system noise temperature changes with time. But let's do this. Let's put a switch here. And we're going to assume for the moment that it's a lossless switch. It doesn't generate any noise, doesn't have any mismatches. Otherwise, we won't be able to do much. But again, you could correct for that, and we're not going to talk about that. That's a detail. What you do, okay, is you put up some standards you know, a hot standard, let's say, and a cold standard, and the unknown noise temperature you're trying to measure. Let's T unknown. Okay. Now, the hot temperature, it's going to be T hot is equal to, or T hot measured is T hot plus TS. Okay, similar. If you switch and measure the cold standard quick enough so that the system noise temperature doesn't have a chance to change, you also measure this. Whoops. Cold temperature plus the system noise temperature. What does that get you? Well, in order to find the noise temperature, you can just divide these two expressions, or the system noise temperature. You divide these two measurements, and you get what's called the Y factor, just for historical reasons, called Y factor. Okay, the Y factor is just the ratio of the measured powers. Now you can do a little algebra, and I'm not going to do it here just to save some time. You end up with TS equals T hot minus Y hot cold T cold over Y hot cold. Okay, so now if you switch fast enough, you can do the same analysis with the unknown, and you can get a Y, let's say we get a Y unknown cold is equal to T unknown plus TS over T cold plus TS. Well, now you have the problem solved, essentially. You know what the system noise is. You know the cold temperature. So with some simple algebra, you can solve this for the unknown noise temperature. And I won't do that. If you're interested in the details, check out the course I mentioned. So now you have a method for measuring noise. Well, what's one of the things you can do with that? Well, one of the things you could do with that is, instead of measuring some black box, you could put some antenna up here and measure the sky. If we have a high enough gain antenna, and if you watched last week, you know that a high gain antenna means in a particular direction, there's a lot more power radiated or received than would be for an isotropic radiator, which means it doesn't receive much from other places. So high gain means that you have a small angular extent that the antenna is looking at. Well, you can measure essentially the sky then, sky temperature, we'll call it the T sky, as a function of, two angles. And then you generate a map of the sky. Well, this is you might call this radio astronomy, which is essentially what you're looking at are small signals that look like noise. This is the technique you would use to measure it. Now, kind of interest of mine is, let's go a detail of a measurement that was made. And that will be in the next part. Hello, now for part 2. What we want to do now is discuss an application of noise measurements. But first we've got to teach a little bit of the history of the universe. It's an observational fact that we looked out on all the galaxies in the universe, that all the galaxies are moving away from us. The universe is expanding. It's an observational fact. We know that because we can measure the recession velocity through Doppler shift. Anybody who's experienced like a car whizzing past with their horn honking, you've seen this effect before. You can use that to measure the rate at which a car goes past you. Same principle as your police radar. The Doppler shift used to tell whether you're speeding or not. Well, in the same way, we know all the galaxies are moving away from us, and the farther away they are from us, the faster they move. Well, you can imagine if you ran time backwards, with time they'd be getting closer and closer and closer with time, until eventually the whole universe would collapse to a point. This point, based on observation, we think happened 13.7 billion years or so ago, give or take, and it was called the Big Bang. This is what we're going to describe a little bit, this little science here. The Big Bang event, at that point, the universe was very hot, very dense, and all there was this compact plasma. Now, plasmas are opaque. So the universe was you couldn't see very far. It's like being in a fog. Light couldn't get very far because the universe consisted of basically free electrons and hydrogen. It was roughly 90% hydrogen, 10% helium, and then a trace amount of lithium and nothing else. Well, then the universe starts expanding at this point. Based on our observations, that must have been what happened. And as gases and plasmas expand, they cool. And at some point, if it cools enough, the free electrons in the plasma join with the atoms, and all of a sudden the universe becomes neutral. This happened about 400,000 years after the Big Bang, based on current models. It's called the Standard Model. So at that point, the universe suddenly became transparent. And we pretty much know the temperature of the universe at that time because we know what type of energy it takes to ionize hydrogen. So we know basically what the light looked like at that particular time is called recombination. Of course, I don't know, that's probably a bad word since they weren't combined before that, the electrons in the nuclei. Okay, so at this point, if this theory is correct, then the observational consequences is that everywhere in the universe you should see a background light that's the remnant of this explosion. Now, this was a hot light, and light, like gases, when the universe expands, the light will cool. So it would be characteristic of a light emitted by a very cold body at this time. The prediction of the Standard Model would be something like the 3 degrees. The first time someone came up with this theory was back in 1931 by the first prediction that this should take place and the nature of it took place in 1948. So if the Standard Model was true, the prediction was there should be a uniform background radiation, and the theory predicts it would be in the microwave. Well, back in about the same time, there was, well, actually quite a bit later, there was this, Bell Labs built this antenna in Homedale, New Jersey for communications purposes. They were going to attempt to do long-range communication by bouncing microwaves off balloons to get long-distance communication. Well, when the first communication satellites went up, that made that whole idea obsolete. So there's a couple guys by the name of Arno Penzias and Bob Wilson decided, hey, if you're not going to use this anymore, we'd like to map the galaxy with it. So they were going to use this telescope to map the heavens, map the galaxy. And so the first thing they noticed, this was a very sensitive telescope now, very sensitive receiver, very low noise figure, they noticed there was this noise that was annoying them. And they didn't know about the prediction at this point of the cosmic microwave background, which is now called, that would be a consequence of the Big Bang theory. So they didn't know what it was. It was going to be a limiting factor in their research. So the first thing they thought, well, maybe it's a terrestrial source, and they aimed it at New York, and they aimed it at other cities. They thought, no, it wasn't that. They aimed it everywhere in the sky, and they couldn't. The noise was the same everywhere. Then they also thought, well, maybe it's something to do with the seasons. Maybe it's something to do with the weather. They didn't see it happened all times a year. Finally, they thought that the noise might be caused by lossy material in the horn itself, in the antenna itself, namely pigeon poop. So they took this thing and they scrubbed the antenna out. They really were looking to see what was the source of this noise, and it wasn't pigeon poop. And I want to do a quote by one of their co-workers that I think I kind of like. He said, Arno Penzias and Bob Wilson were trying to find the source of excess noise in their antenna. Where pigeons were roosting, they spent hours searching for and removing the pigeon dung. Still, the noise remained and was later identified with the Big Bang. Thus, they looked for dung but found gold, which is just opposite of the experience of most of us. That's a quote attributed to Ivan Kamenow, who worked with them. So they met with Dickey and Peebles at the time, who then told them about this prediction. They measured the temperature to be 3 Kelvin, the lower bound, and that confirmed the prediction of the Big Bang model that there should be this microwave background that was around 3 Kelvin noise temperature. For their work, they received the Nobel Prize in Physics in 1978 for this discovery. That's a short, interesting application of noise. This next week, we're going to continue on with this story of measuring noise in the cosmos. to another measurement that resulted in a Nobel Prize more recently. And hopefully it will be of interest. Again, if you want to be a part of our consultant network, write us at info@learningmeasure.tv or learningmeasure.com, and we would like to interview you for this show. And if you have any suggestions for what you think we should be doing, send us email at suggestions@learningmeasure.tv. And if you're a vendor that want to show off some of your test equipment, or give us a press release or anything like that, send us an email at vendors@learningmeasure.tv. I'm sorry this took 2 weeks to get out. We're still learning. Hopefully, my plan is to have this be a weekly podcast, but as you can see, we made a lot of changes. We're working on some more stuff. Like I said, the first few episodes were for working out the bugs, and we're still working out the bugs. Also, announcement, a new course has been put up on our site, Measurement 104, SI Units, Introduction to the Kilogram. I think that's what it is, yeah, 104. And we'd like to get some suggestions on how to make that better. Yeah, one more thing. We really would like some of you suggestions. We know some of you guys are downloading the podcast, but I'd really like to hear what you guys want to see us do here. And also, the other thing that delayed the podcast, I should mention, is the iTunes feed was not working, and we didn't realize that. And it took us a while to figure out what was wrong. It is working now, so you should be able to download the podcast from iTunes if that's the way you would like to do it. Okay, next week, like I said, we're going to continue on with noise measurements and show an interesting application of noise measurements with a little bit more detail. Okay, thank you. See you next week, hopefully.